Now, I want to give some quick remark on the homework questions. So on the recent homework, you saw 4 questions. The first one is to find all the equilibrium solutions of the system. So equilibrium means you are looking for solutions, that means constant solutions. So you are looking for such a vector which is a constant solution of the system. That immediately reduce the derivative to 0. So that means all you needed to solve for the vector field, which is this for the given system. So with derivatives will be 0. So we only need to solve the system of algebraic equations. Here, A, B, C, D, E, F are given numbers. So we know A, B, C, D, E, F. So we are looking for the X, Y functions. So actually constant solution. Okay, so we're going to solve the system. So immediately we see in order for the first equation to be 0, then either E minus A X minus BY is 0 or X is 0. In order for the second equation to be 0, then F minus CX minus DY equals 0 or Y is 0. So we can consider several cases. So the very simple one is that X, Y both zeros. Then immediately we find a solution, which is the 0, 0 solution. Because in this case, when X is 0, right, the derivative of 0 is still 0. So you can immediately verify, yes, that's one solution found. One equilibrium solution. However, if X is 0 but Y is not 0, then we can think of another solution. For example, when X is 0, Y is such a value such that, so we pick this pair. So when X is 0, that's enough for to satisfy the first equation, right? Because this first one is 0 already. But when X is 0, Y is not 0, let's solve for Y. So when X is 0 here, this is dropped, then Y can be found. Y will be F over D. So similarly, we can solve. Okay, so let's recover this equation was F minus CX dy. And similarly, we can assume our Y is 0 and when X is not. So when Y is 0, then we can get in this equation, we can solve for X. Because Y is 0, automatically the second equation is true, then what should be the X X will be E over A. Because when Y is 0, this one is gone. So X is E over A. So we found already other than the origin, right? Other than 0, 0 solution, we have other equilibrium solutions as we have seen here. So let's still look for more because it's possible that these two equations are true. So when this equation is 0, that equation is 0, what will be a constant solution? So let's solve that system. So when we solve this system of two linear equations, we can get xy. Actually, the linear system can be rewritten as a standard form. So as the first equation is simply, if we move to one side, ax plus by equals e. The second equation is cx plus dy is f. So by Cramer's rule, right, if you think of the linear algebra, this a, b, c, d, e, f are the coefficients given real numbers. Assuming the system has a solution, that means a, b, c, d, the coefficient matrix will have a determinant that is non-zero. Suppose we have a unique solution like A, B, C, D determinant is non-zero. So let's try to represent X using Cramer's rule. So X will be okay, so the right-hand side column, EF, in place of the first column of the coefficient matrix, and BD. So you see the X can be represented as determinant of this matrix over determinant of the coefficient matrix. So we can write X. So this, we solve this system of equation to find X already. So then similarly using Cramer's rule, we can find Y. So Y will be, again, by Cramer's rule, very similar. We use the determinant of the coefficient matrix, which is the determinant of that matrix A, B, C, D for the two rows. And then the second column will be replaced by EF. So the first column will stay as is. So that is determinant of this matrix over determinant. So we can find the y value. So based on that, we find another pair of equilibrium solutions. So now let's write X. X, the determinant in the denominator, which is AD minus BC. Yeah, determinant in the numerator is ED minus BF. And for Y, determinant of the denominator is the same, AD minus BC. And determinant of the numerator for Y is AF minus CE. Assuming determinant of this linear system, right, of two equations is not zero. So we can get another pair of constant solutions. Actually, just one equilibrium solution. That in that case, determinant is not zero. We have a unique solution. So then we can find XY. That's one more. So how many equilibrium solutions for the first problem. We can see the first one, origin, and second one, and third one, and the fourth one. So there are 4 equilibrium solutions for this system. So second problem. So second problem is a system with 3 equations, x, y, z. This is a system in normal form, right? Derivative of the unknowns is on one side, and the other side we have y minus z minus 1. And here is x, z plus 1. And then this is a -2, xy. So if we want to find the equilibrium solutions, and immediately we can see, based on the solution, the derivative of x will be 0. That means either y is 0 or z is 1. The second equation also with derivative of y being 0, then x has to be 0 or z being -1. And the third equation, when the derivative is 0, because you're looking for constant solutions, you always remember when we look for equilibrium solution, it's a very special kind. So the derivative terms will become 0, then immediately it's very easy to solve, right, for the autonomous system. So x is 0 or y is 0 from the third equation. So we found some conditions for our solutions. So that means we have to make sure all 3 equations to be 0. So here is what we are getting. Now we just want to make sure all 3 equations to be 0. Then what should be the x, y, z? So now immediately we notice when x is 0, y is 0, you see, when x is 0 or y is 0, then x 0, then all 3 equations will be guaranteed, right, to be 0. So that means we don't have to impose any restriction to z. Z can be arbitrary. So the c is an arbitrary real number. That means any solution of this form with c being arbitrary real number is a solution. So we have found infinitely many equilibrium solutions. That means vectors of this form. Now let's continue. So suppose y is 0, but x is not 0. Let's go ahead, take out this assumption. Suppose y is 0, but x is not 0. So how about x is this one? So we don't have to impose 0 this time. This time we are still assume y is 0, but we assume z is -1. If z is -1, then the first 2 equations are automatically true. And then the third equation, so where y is 0, which is making it, right? That's our assumption because you see y is 0. So with that assumption, automatically the third equation is also true. So that means we have the x coordinate being an arbitrary real number. We do not have any restriction for x. So as long as y is 0, z is -1 here, and the x can be arbitrary real number and still an equilibrium solution because all three are met. All three equations are true. So now we have found another set of infinite equilibrium solutions. So let's continue. Do we have more? So now let's try this case. The next case is when z is 1. Let's take out the assumption of y being 0. Suppose z is 1. If z is 1, of course, z cannot be -1, right? So we have to accept that if z is +1, then x has to be 0 because z cannot be both 1 and -1. So let's assume z is 1, x is 0. Then if x is 0, you see the second equation will be automatically true. When z is 1, first equation is automatically true. And then when x is 0 here, and it will make the third equation also true. So that means we have no condition, no requirement for the y coordinate. So we can let it be any real number because already the three equations are true without additional requirement for the y. So now we have found our equilibrium solutions will be solutions of these forms. Let's include the solution in a set. So any solution of this kind will be our equilibrium solutions. So with A, B, and C are any real numbers. So another problem given in the homework is the reduction of order. So if you have this problem I give as third order derivative is 5x second order derivative plus 2x first derivative sine 3t. So how can we reduce it to first order? So our goal for this problem is to reduce, right? Reduce the equation of third order to a system of equations of first order. And since it's not autonomous, the right-hand side involving t, so we want to have autonomous. So reduce to not only the first order equations, also autonomous system of equations. So you can choose your own name for the new functions because we don't want the second order derivative, right? Because we only want first order derivative appear in the new equation. So we suppose you know already how you're going to invent new names for your new system. So here, suppose we call it U1. And here, this is our U2. And then U3, a second order derivative of x. And that is the name because you're going to replace x. We call it U1 from now on. So as you can see, the right-hand side of the third order becomes, the x becomes U1. X derivative becomes U2. Second derivative becomes U3. So then third derivative will be U3, first derivative. So this equation becomes another equation, but it is first order. So you see the given equation now becomes first order equation. However, we haven't defined U2 and U1, right? So we have to make it more clear. So what is U1? U1's derivative is U2. Because we know this, right? That's not part of the new system, but we know this is our assumption actually. U2's derivative, because of that, U2's derivative is U3. And U3 derivative will be that. Yeah. So this way, do I have still x? No. Your answer, you should not have x because x is already called U1. You cannot keep both x and U1 on the right-hand side the same time. So we already have a new system, right, for the names of x or x derivative or x second derivative. So do not make x appear again because we already adopted new names. So that means once this part, you can still keep them just for your convenience, right, when you establish a new system. But these are not part of the new system. So my remark is that this one is not part of the new system. You see, once you have a new system, you have this, but still there's one more term, sine 3t. So that is, I will erase all that because your x derivative are gone. Or your focus is to find U1, which is x. Once you can solve this system, if you can find U1, U2, U3, but U1 will be found, right? Which is the same as x. However, if you want to do introduce another equation to make it autonomous, here is possible. We just want to give another U, let's call it U0, which is t. So U0, the function's derivative will be 1 because U0, right, is the function which is t. So the derivative of the U0 with respect to t variable is 1. And so since it's already defined, then we can replace that t here. So that's simply U0. So let's replace it. Our goal is get rid of the t variable from the right-hand side. So let's replace this t with U0. Now you notice our U, we got this vector equation. So U which is a vector involving U entries, U0, U1, U2, U3. So now we have derivative of this U, and the right-hand side is the vector field, right? So the first entry is 1, second one is U2 and U3, and the last one is 5, U3 plus 2, U2 minus U1 plus sine 3 U0. So this one is, for convenience, we can remove this part, and then that's the new system, which is now first order and autonomous. So you check your answer if your new systems, if you still have X somewhere after you already named X as U1, for example, if still have X here, then that's not appropriate, because that means you still have some unknown function X. What is X? So that is not supposed to appear again. So it looks like your U1 is a function, X is something else. Then, yeah, you want to make your new system well-defined and clear. So once you name the X as U1, then that X should be called U1 from now on, right? So that's your new system here. So one last problem, second order. So if you have second order and so this problem you can, you have no t on the right hand side, you can just simply reduce to two first order equations. And for example, if you have a system of two equations, each one is second order, then each second order will become two first order equations. So for this system, you will have four equations. So I think, yeah, as long as you properly name, for example, if you think of your x derivative has to be named, right? So if your suppose we keep x as is, we don't have to rename everything. So suppose we keep x still the same name. The derivative of x, let's call it v or u. And the y when we keep as is, derivative of y, let's call it v. So we will have four equations, and the x derivative is u. But the u derivative will be the second order derivative of x. So u derivative will be first derivative of x, which is u, and y we keep as is, plus x squared, we still keep that x, y derivative, which is v, plus y. Y is still. So we have x and u. And then the y derivative is v. And then what is v derivative? V derivative will be second derivative of y. So we can have x, y derivative is v, plus y squared minus x derivative is u. So you see we can get four equations, right? So this is already a reduction of second order to first order. As a result, we get four equations of first order. In this reduction process, we didn't rename x, y. So it's just simply we continue to use x and y as the unknown function. And we keep those two, and we introduce a new name for derivative of x. So we use u instead of derivative. That means second order derivative of x will be just first order derivative of u. Okay, so we use we will replace the y derivative with a v. Okay, just like velocity of another function. Yeah, we call it v. So then we will replace the x derivative, y derivative with u and v respectively. Whenever you see this x derivative, you use u. Whenever you see y derivative, you use v. So then second order derivative will be u first derivative. So, and second order derivative of y will be v first derivative. So then we have reduced the original second order system of two equations to a system of four first order equations. But be careful. So when we have the first order equation, you see the x, u, y, v, right? Are our new entries of this of the system. So we should we should be aware that the right hand side will involve x, y, u, v. Yeah, but all the derivatives will be replaced by u or v.